Hi everyone, in this final video for the Particles and Energy Scheme, which is about lesson 18, atmospheric pressure, we're going to look again at something which builds on what we've studied in the last two lessons, or what students have studied, which is this idea of pressure in fluids being related to particles bouncing off the walls and things like that. And also the density of particles, which we looked at in the lesson before that. So really, there's not much new in this lesson, it's just building on that prior knowledge. But this is a nice lesson because, again, this links directly to things that students will study later on when they get to year 10 and 11, especially if they do triple science. And it gives them a really nice way of thinking about how to solve some really difficult problems that they'll encounter later to do with pressure changes as you go up into the sky in an aeroplane or something like that. So it's really important, both to build the concept of particles, but also to prepare them for later on. It's also a nice chance to introduce them to a great story from the history of science and just reinforce that guess, deduce, check model that we looked at right at the beginning of this unit. And I might start this lesson by going back to the diagram that I drew right at the start of the unit. Let me just move my cable, apologies. So I might start them off and just remind them of this model, remind them of the mystery boxes, something like that, and just kind of go through that process by which scientists come up with scientific knowledge. And I might also remind them of this picture of the Earth that the ancient Greeks had. This idea that of the four elements, Earth was right down at the bottom, surrounded by water and then air and then fire, and then this kind of unchanging cosmos around the outside. Because what we want to do in this lesson is contrast this ancient picture with a picture that was suggested by an Italian natural philosopher. I won't call him a scientist because they didn't really exist back in the 16th century or whenever this was, 17th maybe. He was a natural philosopher who was pondering the nature of the universe and these big questions. And he was one of the first people to come up with what, in this unit, we've been calling a scientific guess. So I'm going to lay this out in exactly the same way as I did in the first couple of lessons. And I want to introduce Torricelli's guess as follows. So Torricelli was the first person to posit the existence of an atmosphere. So he said, well, okay, we're pretty happy now that the Earth is this round sphere. And I'll label that as the Earth. And what Torricelli suggested was that if you were to draw something like this, he imagined there was this kind of sea of air all the way around the Earth. We're kind of smothered in it, a bit like if we were underwater in the sea. Well, actually, we're under this sea of air, and it's all the way around the Earth. It pervades the whole thing. And nowadays, we would call that the atmosphere. But Torricelli didn't have that kind of language to talk about. He was just kind of groping in the dark, trying to work out a picture of what it looked like. So he described it as a sea of air. And I might label that on the diagram, or actually I'll just say that. And I think it's a nice phrase that students can remember. Now, what would you expect to happen here? Well, what Torricelli and Pascal, who is super famous, and obviously you can tell students that the units of pressure are named after Pascal, and we'll see why in a minute. But what they deduced was as follows, that if you were to take a cross-section here like this, if you were to take a cross-section like that of this sea of air that seems to surround the Earth, well, the way I've drawn this in the past is a bit like this. And again, we're just going to build on the ideas that we started to introduce last time in the liquids lesson. Pressure in liquids. So if that's the Earth there, I can label that as the Earth. That's at the bottom of my cross section. Well, Torricelli argued that the air up above should be pushing down on the air down below. They had this intuitive sense of things pushing down and squashing each other. And the way I've tended to draw this in the past is just to shade it very lightly up here, but then as I go down, start to shade a bit more firmly, and then as I get down right down to here, shade much more firmly still. And that's not maybe the best diagram, but hopefully you can see the idea. And it's worth stressing to students that at this stage, these guys didn't have a really clear picture in terms of particles. They weren't thinking in terms of particles. But what we can do now is kind of give them the modern account of what this might look like and say, well, if we were to think of this in the kind of terms that we looked at last lesson, what they would expect is as follows. If you were to draw something like this with that as the Earth down there, well, if our particle model guess was true and there is this sea of air surrounding the Earth, well, what you'd expect, as we saw last lesson, is that the particles down here, I mean, they're the particles of a gas, so they still should be a little bit apart from one another, like that. But you'd expect those to be more densely packed than the particles up here. And all you want to do when you're drawing this diagram to students is just fill in the gaps here and kind of, if you can try and get that gradual decrease in density. I might add another couple of particles down here just to emphasize the point, like that, and show that it's much more dense down at the bottom than it is at the top. Now it's tricky when you're drawing these diagrams because it's going to look a bit like a liquid down at the bottom and more like a gas at the top. What we don't want students to think, we don't want to give them some sort of ancient Greek picture that actually it's a liquid down at the bottom and a gas at the top, water and air. So it's worth stressing to them that we're talking about gas all the way up because it's a sea of air. And you know, you can add some labels here if you wanted. You could say less densely packed, more densely packed, less densely packed, and so on. But what's really important here is that we think, well, okay, how are we going to test whether this is true? How are we going to test whether Torricelli's sea of air hypothesis, model, guess, whatever you want to call it, is correct? And this is where it's nice to tell them a story about Pascal. Whether it was Pascal or his brother-in-law who did this experiment is disputed, but anyway. So Pascal lived in France, and he decided he wanted to test whether what Torricelli thought about the atmosphere, and we can see from here, was true. So he decided he was going to measure the pressure at the bottom of a mountain called the Puy de Dôme, measure the pressure down here, and at the top of a mountain called the Puy de Dôme. So he decided he was going to measure the pressure down here and measure the pressure up here. Now, your students who are particularly keen, you might want to tell them about the early barometers. So barometers use mercury, and the level of the mercury rose and fell, depending on the pressure of the air, which is all very interesting. It's also, it creates a vacuum, and this was really mind-blowing at the time because in the Aristotelian picture, a vacuum couldn't possibly exist. Anyway, you might not want to go into that much detail, but I think telling them that this experiment was actually done to see whether, if you went high enough in the atmosphere at the top of this really, really tall mountain, you saw that difference in pressure. Well, lo and behold, what did they find? They found that the pressure was higher down here, higher pressure, lower up here. And again, it's just a nice way of going back to that scientific method that we introduced at the beginning of the scheme with the mystery boxes to say, well, okay, if this is our check, we guessed there's a sea of air, we deduced we'd expect the air to kind of push down, or in the particle model, more densely packed down here, less densely packed up here. So we should be able to measure that with our barometer. And what we found, lo and behold, is that there is a high pressure down here and a lower pressure down here. So we can say this is correct, and it's just a nice confirmation that our model of the sea of air and the and indeed the particle model could still be correct. So it's a really nice simple way of reasserting the guess-deduced check model, but also reintroducing this idea that the particles are more densely packed down here and less densely packed down here. Now, what you'll see in the lesson is that the questions all refer to what's in this picture, and that's the end of the scheme of work. And I hope what you've got out of teaching this scheme of work, if you've made it this far, is that all of the lessons keep coming back to one or two really, really core ideas, what you might call big ideas, or the underlying concepts. And for me, those underlying concepts are, and it's worth stressing this to students, they are the particle model, that all matter is made of these tiny particles, the arrangement of which determines the properties of the matter. And then I think this other really, really important idea is about the particles' energy and how they move and how that links to things like temperature and pressure and so on. So hopefully by the end of this scheme of work, students will really have a good grasp of those two core ideas about particles and energy, and they'll be ready when they get to GCSE and start studying chapter 1 and chapter 3 of the GCSE unit. They'll be ready to start applying some mathematics to think about this in more depth. Thank you, and I hope these videos have been useful. There will be more to follow for other schemes of work.